Pandurangan from the Department of Computer Science and Engineering, IIT Madras. We will be delivering a series of lectures with emphasis starting from algorithms, basic algorithms, advanced algorithms, and cryptography. This is the first series of lectures which is planned for today and tomorrow, where we will be talking about algorithms. Over to Professor Pandurangan. I don't like to take much of your time in start of the session.
Thank you. Thank you for the invitation and the opportunity. I already had visited here and have spoken. I have given a glimpse on various paradigms, how the problem solving, etc., need to be effectively done, and so on. I had also visited Mysore and gave for the training program certain modules. After doing these two, we sat through various discussions and then finally identified that in order with the Campus Connect program also in mind, a thorough, systematic, slow and steady paced comprehensive coverage on these topics be done, and those who would like to pick up the topics at a later point, they can use the cafeteria model where they can select a particular topic and go to the appropriate level of detail as shown in this discussion. Therefore, the coverage that we are going to have in this series will be simple, slow. It will have all the details. I am not going to skip any detail, and it is targeted for the Campus Connect audience, namely the first time listeners in various rural colleges and the colleges which the Campus Connect program reaches. Okay. Since it is going to be exhaustive, surely people at various level will find useful on various sub part of it. Except for the students who are trying to graduate, the topics that I cover may not be what should I say, you might know some of them, so the entire topic, the broad range of topic may not be appropriate for you. Therefore, use your discretion. I will give the description of, to begin with, I will give the introduction, and after that every time I will tell you what is that I am going to discuss, what are all the concepts and ideas I am going to emphasize, and if you are already familiar with that, you may skip those sessions, and those sessions on which you find that it has something new for you to learn, you are most welcome. Of course, you are welcome to sit through all the sessions, that is no issue here, but I would like to alert, because the objective of this series vis-a-vis your position on the content and coverage is to be first explained, and that is the reason why I am taking a minute off and then telling you about how this coverage is going to be. Okay. So now let us begin the discussion. Let me ask you the following question. What is the fundamental attribute of human race that distinguishes from animals? Could you give me some response on this? The fundamental attribute of human race that distinguishes from animal. Of course, we can say we know to laugh, whereas most of the animals do not laugh, and so on. Fine, that is one kind of physical. Now, could you list some fundamental way in which the humans differ from any other animals on earth? Intelligence. Okay. So, most of the animals also have the intelligence. They do hunt, and they do workout strategies to grab their meal. They have variety of strategies for living, and so on. They have some limited intelligence. Intelligence is certainly an aspect, but which aspect of intelligence that we seem to have, which at least the animals do not seem to have? Okay. So, most of you have several suggestions, and what is the essence of all this thing is the ability to imagine things. Okay. Most of the animals, they are very reactive. If they see some threat, they will react to it, whereas it is possible for us to imagine. Not only we can imagine, we are also able to derive patterns. Day in and day out, when we observed several stars and moon and their movement, we are able to see some pattern in them. We could see that after 365 days, the sun appears to come to the same point in the sky and so on. And so many observations we have made over a long period of time. So, from the sporadic observation, we are able to extract some kind of a pattern. This ability to extract pattern from seemingly disjoint event, or what is known as abstract thinking, is one fundamental attribute of human race. And because of this abstract thinking, many of the problems human beings are able to formulate in a very different way. Suppose you would like to build a temple, or you would like to establish the city facilities around variety of streets and other facilities of infrastructure in the city you would like to build. Immediately, this particular problem which you want to solve, you are able to abstract out and get into certain representation and so on, and this ability of human beings is something which is very distinct. And what would you consider the second key ability of the human race, which is there in other animals also to some extent, but then humans have distinguished in that? Yes, this communication etc. comes in the abstraction that we have mentioned. So, basically for instance, when you see certain 3 lines, you have to somehow convey the quantity 3. Earlier we used our fingers, and then we may say we may not have even a vocabulary for lines, so we may act like line and then say like this to convey that 3 lines are there. Later on vocabulary was built, representation, notation. All of them are the derivation of the power of abstraction. We are able to think in abstract terms, represent, analyze, and that is one key ability. And what is the second key ability of the human race? Yes, that is observing, creating the patterns and then seeing the pattern, etc. That comes under learning. In fact, learning experience itself is an abstract process. The change is not physical, it is something mental, right? That you know something is an internal state of awareness and its change. The second one is physical. Where is that we excel? It is physical. What is that? Self-awareness. Well, that is also into the intellectual realm. What is that? Yes, yes. So could you generalize it? Using tools. That is hitting the nail on the head. Okay. The second one is using tools. These are the 2 fundamental attributes of the human race. The topic that we are going to see connects directly to these 2 fundamental attributes of human race. That is the reason why this is at the heart of computer science, and this is really forming the core of the entire body of the knowledge on which everything rests. Okay. So, with abstraction, we try to formulate mathematical problems and then we solve problems. Computer is a tool for solving problem, and we are interested in using computer as a tool for solving problem. We have devised the tools like wheel, and certain things we might borrow from nature, certain things we might create, and so on. Okay. And whenever we are trying to use any tool, because it is a physical activity, there is something which is very inherent that we look for. Okay. The fundamental thing that we look for, okay, besides the functionality and aesthetics, is its efficiency, how well that tool is used, how effectively that is serving the purpose. Okay. This is the fundamental quest in the human mind. The moment I devise something, I would like to make the best use of it. Okay. And this topic, algorithms, is going to touch upon all of them. Both abstraction and using of tool will form the fundamental activity, the core activity in the study of this topic. Okay? That is the reason why this is admired as the core or heart of computer science. So let us get to the way in which this is relating to the entire body of knowledge. If you look at the way in which we have acquired knowledge, we codify them as meta science, philosophy, mathematics. They are all meta science. Okay? Physics, chemistry, botany, zoology, you can call them as kind of a natural science. They address the natural phenomena, physically existing objects in the world, and studies on them. And the third category is engineering, tool design, making it functional and operational, and so on. That's the reason why we have meta science, natural science, and engineering science. Again, if you look at the way in which the algorithms are looked at, the problem solving process is looked at, all the three of them and all their contributions are coming into this field. And that is the reason why there are a lot of subtleties here. Without understanding those subtleties, it is impossible to really gain mastery in this. You can get a nodding acquaintance in it, but to get to the mastery, you need to appreciate that it is really cutting across and touching upon every aspect. And without having this all-round knowledge, it is impossible to build the sharpness and the command over this topic. That is the reason why in my development, I am going to touch upon all these three aspects. Okay? So where do we begin? We begin with the principles which touch upon all of them. Principles form the blocks of any body of knowledge. Principles of mathematics, principles of physics. Anything if you take, for instance, the principles that define the fundamental building blocks. Using the ideas and concepts which are enumerated as principles, the whole body is developed. Any deviation from the principles will lead to absurdity. Strict adherence will lead to logically coherent and practically valuable piece of information. That is the reason why when we begin any new body of knowledge or its awareness, we must start from the principles and then go about systematically in using them as powerful building blocks. Okay? So, what are all the principles? What do we get under principles? What are the issues and topics that are going to be addressed under the banner of principles of algorithms? Again, first of all, we have to see that algorithms is meant for solving problems. Computers are used as a tool for problem solving. Therefore, we must begin with the notion of problem. Typically, by the term problem, we mean a question to be answered or some difficulty that we encounter. Something like my car has developed a problem yesterday, right? And what do you think of this? These kind of things are generally called as problems. But such a generic definition is inappropriate in our context. In fact, by problem, what we mean is only a computational problem. Computational problem. If at all you are seeking a solution for a problem using computers, it has to be first formulated as a computational problem. If certain things cannot be formulated, then it is impossible for you to use computers to analyze that entity or solve problems related to that. That is the reason why questions like existence of God, world peace, and so on, you cannot have a computer-based solution, or a reasonably computer-based analysis is feasible or even possible for these type of questions. The reason is they don't lend themselves to proper mathematical modeling. Perhaps Bertrand Russell's famous paradox on why the concept of God cannot be mathematically modeled, it's not only funny and intuitive, it also reveals certain subtleties when we try to represent in certain concepts in the mathematical world. He gives a proof that God is not omnipotent. Omnipotent means he can do anything. If he can do anything, he can create a stone which is so heavy that he cannot lift. Okay? Now the question is this: if he cannot create such a stone, then creating such a stone is impossible for him. And by the very definition, if he could create a stone, lifting that stone is impossible for him. In either case, I have found out one scenario where God cannot do something, therefore God is not omnipotent. Okay? So when he gives this argument, what he wants to say is that look at the way in which when you try to model some of those things into a mathematical framework, it just will not get into a proper logic. And that is the reason why you cannot manipulate them in a systematical mathematical framework or derive any sensible theorem on God. You can have theorem on integers, but you cannot have theorem on God. Okay, the main reason is this. Okay, so basically by a computational problem is the following. Every computational problem is required to work on certain values which we call input, and it is required to produce certain values. So work on certain values. It is required to produce some values, and this is called output. The general specification of the computational problem has the following. So we need to have a specification. The specification of the computational problem consists of the following: on what kind of values it is going to work on. Okay? So specify input. This allows you to identify clearly which are the legal quantities on which it can work and which are the illegal quantities, which are the valid one and which are the invalid ones. So clearly we have to specify the values on which the computational problem is supposed to work. 2, you describe the properties of output. 3, you give the general description of the relation between input and output. Give generic description of relation between input and output. All these things should be done. For instance, you may say, yeah, question there, yes.
When you are at the stage of formulating a problem,
Yes.
so let's assume there is a so-called hard problem. So when we don't know if it is solvable or not, or whether it will have an output. The second point about properties of the output, is it at that stage, can we talk about that?
See,
We don't really know what the output will look like.
we may not know what the output is going to look like, but we must at least have the end in our mind. What is that you want to do? You are working with some values. What is that you want to obtain? Whether it is obtainable or not is a second question. Ultimately, what do you want to get done. That is what is part of the specification of output, or what I mean by properties of output. What exactly you want out of this process, right? Whether that is obtainable is a different issue. Whether that can be efficiently obtained or inefficiently is a different issue. What process gets it done efficiently, what process gets it done inefficiently is again a different issue. But first, we must begin with a very clear idea of what is that we would like to get at the end of the solving of the problem. I may not know the values, right? But I will know the relation between this input and output. In what way these are related. Okay. So this generic specification, if you are able to obtain, then there is a hope for you to solve this kind of a problem using computer. If you have vagueness, fuzziness, or if these things are incomplete in some respect, then the formulation itself is sloppy. Therefore, you will encounter a lot of difficulties when you proceed with tackling that particular problem. Okay? So what is very important for us is we need to have this in our hand. So this is as far as the computational problem is concerned with. And where is algorithm coming into picture? Algorithm is any computational procedure. The concept of algorithm is different from concept of the problem. We are in fact going to match these two appropriately. Okay? So algorithm is any computational procedure. Okay? What we mean by computational procedure is the following. At this juncture, I am without getting into the formalism, I would like to express the following. The property that algorithm is finite, it is terminating, it is unambiguous, etc. I give the English level description rather than the formal description. The formal description is possible, what we mean by a computational step. What do you mean by finite time? Everything can be made precise provided we have the appropriate mathematical framework. Say, for example, concepts like Turing machines can be used to precisely state what we mean by a step. At this moment, we use an informal terminology of a computational step. The computational step, what we mean by computational step could be manipulation of some point and a distance. It could be finding multiplication of two numbers. It could be comparison. It could be anything that you are doing in terms of computation. So by computational step, I mean a very generic operation that you are doing on mathematical entities. Although this looks very different, computing a distance between 2 points looks like a geometric operation. Searching an entity in a database looks like some comparison and so on. And adding two numbers and computing some values looks like arithmetic operation. Although they all seem very different, they can all be unified. They can all be reduced to the barest minimum of certain very simple operation done on abstract machine, and that is what Turing has achieved. The Turing machine concept, which was introduced, is a phenomenal idea in the sense it can talk of computational step without even talking about the problem domain, without talking about the mathematical entities you are manipulating, because everything gets represented in abstract symbols there. Every computation has been transformed into state transition over there. So whether it is a geometric problem or a database problem or something like that, it is possible for us to define it. And that is the reason why, for a deeper study on the properties, you need to go to that abstract model. However, from the practical perspective, we don't have to really go to that level at all. It is much like, in order to use a computer using, let's say, Pascal or C, you really don't have to know the architecture or inner details or something like that. If you know the standards, C standard or a Pascal standard, and you can code it, and then you can run the code and work with it without knowing really the internals. However, if there is several kind of advanced error and several other things crop up, then you get into the architecture, then you look into the why the buffer overflows, what is the size of it. That is when you really get deeper into the system. Until then, you really don't ask the question about it. So in the same way, what we can do is, we are going to appeal to the intuition of what we mean by computational step. So a computational procedure is a sequence of computational steps. So by computational steps, I mean mathematical manipulation of mathematical entities. It could be vertices in a graph, it could be points in a plane, it could be any mathematical entity, elements of a set. It really doesn't matter. They are all so it consists of a sequence of computational step, and we would like to qualify it so that we connect to the real world scenario. So we would like first this sequence to be finite sequence, and we also want the steps to be unambiguous. In other words, there is only one meaning for it. The reason is, we are now looking into the process of mechanically executing this. If there are multiple interpretations possible, obviously the machine cannot execute it, and that is at least the principle with which we are working. People who are working in artificial intelligence are soon going to contest such a decision. But for all practical purposes, we will not dwell into, or we will not digress into that part. What we look at it is the mechanical way of doing it. That means there should be only one way of interpreting anything. When you say do this operation, that should result in only one value, and there should be only one way of doing it. And that is what we mean by so there is a finite sequence of computational steps. Each one is unambiguous, and again every algorithm has got input and it has got output. All these notions are available for algorithm also. So how are we going to connect the notion of algorithm with the notion of problems? Yeah, question here?
Forgive my ignorance there, but when you say finite steps, again there is that question about, say, if there is an iterative kind of algorithm.
Yes.
So that basically says that you are tending to the solution, but you will not actually reach the solution. So there, would you call it finite, or is it the accuracy is a function of the number of steps?
That's right, definitely. So what we are going to do is that we will what we call those type of things is called a schema. In other words, it is a parameterized, and for each given specific value it will be finite. But then my specification is going to be parameterized over different values. So for taking continuing with your example, if let's say it is a numerical methods of iteration, Newton-Raphson method, for 0.1% error, you may have to iterate 20 times. If you want to have 0.001 level accuracy, you may have to iterate 50 times. Okay, but for any given value, this is finite. So we will have the relation between the error tolerance epsilon and the number of steps as a function of it. And as long as this function is finite for every given epsilon, we have now a specification of a schema. Okay, and in practice, whatever is the limit to which you can obtain, you get to that value and it becomes finite up to that point. However, our specification is not tied up with those special values. That is because today you might be interested in 0.1 accuracy. Later on you might be interested in 0.0001 level of accuracy. So I don't want to freeze my specification only for 0.01 and say that for 0.01 you do this. Instead, what I would say is, for in general an epsilon level of accuracy, you may have to iterate this many times. In that epsilon, if you substitute 0.01, you would get whatever you want, and 0.001 you would get for the other context. Okay, so that is how it will be. So what I mean by finite is, for every input instance it is going to be finite. So how are we going to tie up these two? There seem to be a lot of similarity. We have the notion of input, we have a notion of output. This also working on input and then it is producing an output. Okay? So the way to connect these two up is viewing algorithm as a way to realize this relation. Okay? So there is a specification and the algorithm is attempting to work on this. The algorithm may be correct or incorrect, but still it can be an algorithm. For instance, you may say sorting. You might have written some steps. It is a computational procedure. It takes some value. It produces something as an output. It has taken the value, let us say 257, and it has produced the value 527. So it has terminated, it has taken finite time. It is an algorithm, except that this is not an algorithm for sorting. Sorting should output smallest number first, the next larger next, and so on. It should output the values in the increasing order. Unfortunately, it has given the values in this way, therefore it is doing some rubbish. Okay? It is not a correct algorithm, but still it is a definition of an algorithm. It does some steps, it takes some input, and it produces an output. So where do we connect the notion of algorithm with the problem? This is where the notion of correct algorithm comes into picture. An algorithm is said to solve a problem correctly if the algorithm takes the input specified by the problem or legal inputs to the problem and produces the output which is specified in the problem. Therefore, there should be a match between the performance of the algorithm and the specification of the problem. If the match is identical, then the algorithm is said to correctly solve the problem. Otherwise, algorithm is doing something and it is not anything to do with the problem you have in your hand. So that is buggy and you may have to fix it, right? So this is how these two notions are related. So we have the abstraction. We have a real life problem. The real life problem is converted upon abstraction into a mathematical problem, and we have the specification of the mathematical problem. Once the specification is available, we go about obtaining this output for certain input, because we would like to solve the problem in practical instance. Okay? I may have in general for if you want to build a tower of height x, you have to build a foundation of depth y. I may have some generic formula. Now, I would like to build a multi-story building of 200 feet high. How much foundation I have to dig up here? So you give 200, that becomes the input instance. My general specification will have, okay, how they are related. But for a particular one, you will be given the value and then you will obtain the corresponding output. In the earlier days in mathematics, the specification of the problem and the procedure which is working on it were more or less merged in a seamless way. And that is the reason why there is a confusion even in our computing world. Our first language called Fortran is formula translation, which means every computation will require you explicitly specify what is that formula. Basically, if I say f of x equal to 2x square plus 4x plus 3, it means multiply x with x, multiply that with 2, with that add 4 times x, with that add 9. That is what it means, and you are saying that as a formula, and that formula is to be translated. So you store x, you manipulate the values, etc. That means the specification itself has got, in some sense, in some tacit form, the algorithm as well. Okay? And that is the reason why we couldn't distinguish between these two notions in the early days. And because of that, there were a lot of confusion. Especially when you are taking, for example, sorting. In sorting, what you are giving is only the specification. I will give you some 100 numbers. All I want you is to produce 100 numbers rearranged in such a fashion that you have to get them in increasing order. This is the specification of the sorting problem. This doesn't tell you how to go about it. So there is no formula translation here. For matrix multiplication, there is a formula translation. There is a formula for multiplying matrix. You just have to type in those equivalent computation and you get a program also for it. So looking at the specification itself, you can write the code. That is the reason why it is called translation, formula translation. Not so for sorting. You look at the specification, no amount of staring will lead you to any algorithm. You have to really think about, okay, how do I go about rearranging the values so that finally I am guaranteed to get items in increasing order, numbers in increasing order. So now here you have to work out the algorithm. You have to worry about the computational procedure. What should I do in order to do this? Traditionally, mathematics had two flavors of building the argument or solving the problem. One is existential and another one is constructive. Most of you might have heard about Rolle's theorem, mean value theorem and so on, which says there exists a theta, right? Suppose f is a continuous differentiable function, there exists a theta that f of a minus f of b by b by a, b minus a, okay, f dash of theta is, there is a theta in the interval satisfying this condition. It says you have a proof for them, you are convinced of that. So there is some logical argument advanced to you to convince, but after reading the theorem, if I give the function 3x square plus 4y plus 2 and if I give the interval 736, will you be able to find the theta after reading the proof of that theorem? You will not be. The reason is it is not constructive. It is only a bunch of logical argument that existence is guaranteed, but how do you actually find it? And that is where these kind of computational procedures have started taking importance. So people used to divide mathematics into constructive mathematics and existential mathematics. But not until computers have come into picture, these constructive mathematics has become an object of engineering delight. And this is where everything was carried into labor, effort, money, time, everything it is converted into that. If there is a computational procedure which is taking 10,000 years, obviously you would not like to write a program based on that steps, that sequence of steps. It could be unambiguous, it could be finite. But if that finite is 7 trillion, you would not like to use it. If the same problem can be solved with 7,000 steps, you would like to go for that rather than the 7 trillion steps. Therefore, this is where the efficient use of the tool comes into picture, which means we have to now quantify what we mean by efficiency. Okay? Because I want to make an effective use of computer. What do you mean by effective use? So, like any other way in which any other science has grown, how does anything has happened? Okay, even the seat table that you are sitting now, okay, how did it happen? Some solution will be found out. Okay, maybe a broken trunk or some tree. Later on, if you sit there, it will be very rough and then it could be very, hurting. So what you do, you take a stone and then rub on it and make it smooth. But you might sit on it, but it could be either too high or it could be too low. Then you try to adjust it. And so over a period of time, the solution gets refined. Now you talk of ergonomics and ergonometrics, and then what should be that for typical human beings, how high it should be and how the resting points should be and everything you talk about, and you now design a table, chair and all. We did have place of resting, place of sitting from the ancient days till today, but you see how it gets refined over a period of time. Okay? So anything, we start with some solution. It will be very crude. Later on, we build some understanding. Then we codify some of the general methods which can be used to identify or recognize certain aspect of it. Then comes the brilliant flash of good solution. And that understanding brings in a lot more ideas flowing into it. And this is how the science grows. Computer science, as well as the notion of algorithm, is also no exception to that. Efficient use. The first rush of the blood to your head, what does it say? Efficiency means time. So faster the algorithm, good will be that algorithm. So what do? I write a program and then run it and then see whether it is running fast, and if it is running fast, I say that I'm very happy with the algorithm I have. That is what was virtually happening. Okay? So in the mid 60s and late 50s and mid 60s, people used to publish, because Fortran has come into picture, they used to publish programs, an efficient program for sorting. Somebody would publish a code and people will try to adapt. But somebody else would come up with another code saying that my code is better than his code. Okay? And in order to substantiate his argument, he would take up some three inputs. It is there, it's a part of the history, it is there as a record, black and white record. Okay? You'll run on 3 inputs, and then on all the 3 of them he will argue that his is taking x millisecond, somebody else is taking y millisecond, look, x is smaller than y on these 3 inputs, therefore my method is better than his method. That is it. Okay? Then, and the other guy would again come up with a counter argument saying that those 3 looks like some freakish exceptional. Look at these 5 inputs. On this, mine runs faster than his. So this kind of claims and counterclaims were flowing around. That is because there was no scientific basis for assessing the merit of the algorithm. Simply saying that runtime is going to be considered as the hallmark of the quality was leading to very big chaos. The literature is full of claims and counterclaims, and people were thoroughly disillusioned with this. And that is when Professor Knuth, he is now a professor emeritus in Stanford. Okay, he is Donald E. Knuth. He is the person who gave us TeX, okay, the famous text processing system, probably the commercial version of LaTeX and other things you might be familiar with. TeX was the brainchild of Knuth, and he is considered as the founder of the area called algorithm, because it is he who has enunciated the principles, starting from the notion of the problem to the notion of the algorithms. He went about making certain things much more systematic and cleaned up the fundamentals and defined clearly the yardstick based on which you have to measure 2 algorithms. The moment you have this kind of a measure, now you can be lot more scientific. What was happening earlier, the way to discover a good solution is, suppose you have 3 solutions. You write 3 different programs, run all of them, find out which one is running fast, okay, and then identify the fastest one or the most efficient one. Okay? If a civil engineer does it, you will really call him as a at most stupid guy. Suppose there are 3 possible materials to construct a house. Which one is going to cost less? And if he builds using material 1 one house, material 2 another house, and material 3 at another house, and then declares that this particular material costing much less, would you appreciate his efforts? That's what we were doing. The way in which we were discovering an efficient solution when multiple solutions are around was write program based on every idea. That is because I don't have a common measuring stick. I don't have a measure to assess it. So the only way I do is run the program and then find out which one is good, right? Which is totally counterintuitive engineering practice, but that was the only option available for us until Knuth gave the principles out. It is he who made it systematic, and this is the starting point of the formal description of the area. So I am going to expand on the concepts that Knuth has proposed as the fundamental principles, and then list out the concepts one after another and complete the description. So the 2 notions that we have seen, which is giving the seed, is one, the notion of problems, secondly, the notion of algorithms. and now we are interested in the effectiveness of the tool. Okay? So, Knuth also started with the following common sense perception. Yes, you say one algorithm is better than other algorithm if it takes less time than the other. But the point is, how do you assess whether one is going to less time or more time? Just use your common sense. What is the time made up of? The time is made up of executing the instructions. It is that which consumes time. Therefore, why don't I count the number of instruction in a particular procedure? That was the starting point. So what he suggested was the principle number 1, use instruction count as figure of merit. The moment he said this, now I look into the procedure. I am not even going to look into the program, or I am not going to even run. So well before I write even the code, I look into the idea. Okay? The idea says do this and that. I forget whether I am using an array A name or a temporary variable, what is the name of the procedure which is calling. I don't have to even worry about all those things. Even before I think of even the programming language or the code, I look at the idea. Do this, this and this, and you will solve it. That's what you are saying. And you are saying all in terms of computational steps. How many steps are in this? Let me count it. Okay? So let us take sorting. You have an idea A. Look into how many comparisons are done in that. 10,000 comparisons are done in this. It's another method. 200 comparisons are done. The same input, you see that it is getting done. Take another input. That is taking 40,000 comparison. And here it is taking only 350 comparison. Looks like by looking into the steps count itself, I am able to get an assessment on the quality of the algorithm. Okay? So this is his first principle. The first principle is instruction count should be used as the figure of merit. Okay? So this is called time complexity. This is not the running time. Running time is something which is physical. It is measured in seconds, time, year, okay, light years, anything. Nanosecond to light years, you have several ways of measuring the physical time. This is conceptual. That is why this is called a time complexity. So he introduced the notion of time complexity. Of course, this notion, if you want this to be really meaningful, it should bear some relation to running time, right? If your model is inappropriate, then your conclusion will also be nasty. Okay? For example, when we modeled that Earth is flat, we could not explain why eclipses are occurring. When we modeled that Earth is the center of the universe and whole galaxy is running around us, we were not able to explain why sun is again and again coming near one particular star after 365 days. Okay? Then we realized that Earth is not the center, and so on. Okay? That is a stupid way of modeling the space and the celestial bodies and their movement. Okay? That model was not explaining realistically some of the phenomena, so that was abandoned. Some other model was evolved. Okay? So what is important is when you try to enunciate a principle, the time complexity should truly reflect on the running time. Just because I am a famous mathematician, I cannot simply say, you take this as time complexity and ask you to work on that. Because if that has nothing to do with the actual running time when you run the code in practice, then they will throw away your concept and ideas. Okay? Therefore, it has to be chosen in such a way that the time complexity has a bearing on the real life running time when you actually implement. When you take it to the implementation, the conclusion you get here should agree with what is happening in practice. Only then that concept would survive. Otherwise, that concept will be thrown out. So let us see what he did. So instruction count as a figure of merit, and he says instruction count is called time complexity. Okay? And the second notion that is important is what one of our colleagues here has already raised, right? The finiteness. When you say finiteness, for what kind of input, for how much quantum of input? Obviously, depending on the quantum of input that you process, the labor you are working with increases, right? If you want to have 0.01 level of accuracy, you do some amount of iteration. But if you want to have 0.00001 level of accuracy, you have to iterate more. It's natural. Okay. Therefore, more the demand, more the labor will be. Hence, we need to first of all freeze the idea on the so-called input size. How much item it is processing. Naturally, the labor that you are using in your computational procedure will have some bearing on the quantum of data you are processing. Take sorting, for example. You can intuitively feel that sorting 10,000 numbers will call for a lot more labor than sorting 10 numbers. And sorting 1 million numbers will call for a lot more labor than sorting 10,000 numbers. In general, you must quantify how much input you are taking to process, and for that quantum of input, how much labor it incurs. Okay, that is what will give you the so-called time complexity. Because when you want to compare, you should compare on the fair basis. You cannot run one algorithm for sorting on 50 numbers and another algorithm for sorting on 200 numbers and say that this is faster than that. Obviously, that is a meaningless comparison. Therefore, when you want to compare two methods, you must provide a common footing for them, and that requires you to freeze the notion on input size. How much quantum of input you take to process. This is fundamental notion. Therefore, input size is something that he introduced, and we need a way to quantify the input. And this has become a very tricky job. Okay? For certain things, it became very easy. For example, sorting, I have told you, sorting 10 numbers, sorting 20 numbers, sorting 10,000 numbers, sorting 1 million numbers. So what can work for us as the quantum of input? The number of values you have taken can work as a measure for input. How much input you are processing? 10 numbers, 20 numbers, 50 numbers, 1 million numbers, and so on. So the number of items you are taking as an input can act as a measure for input size. Not all problems work this way. There are some instances, there are some subtleties involved here where it is not the number of inputs that will serve as the measure of input size. Something totally different is needed. Okay? Take, for example, the same one which is proposed by our colleague here. The number of iteration is depending on the accuracy. Accuracy is going to be only one value, right? Epsilon is one number. Whether that is 0.01 or 0.001 or 0.00001, it depends on that. So depending on certain values, the labor increases. It is not depending on the number of values that you take. I will give another simple example. Very well known example you would have done in your school days. Finding the GCD of two numbers. Given two integers, you find the greatest common divisor. Okay? So when you give small numbers, you can find the answer quickly. But when you give large numbers, you have to work lot more steps to get the answer. Whether it is large or small, how many numbers you take? You always take only two numbers. Okay? So the saying that here 2 is the input size is inappropriate, because whatever is the input, you will always have two numbers only. So the number of numbers you give for the algorithm would measure the input size is meaningless, because there is no variation. 2 is a constant. What varies here? What varies here is the value you are using. So as the value increases, the labor you are putting in also increases. So what captures that increase in size? You have to use that for input size, not simply the numbers. Okay? So for sorting, the number of numbers is okay. However, for finding GCD of two numbers, 2 cannot be used because 2 is fixed. You cannot map 2 to several quantities. So what is the varying quantity there? The varying quantity is the value. So how do you measure the variation in the value? How do you relate that to the input size? The natural way to use is the number of bits needed to represent that. And that varies. When the value becomes larger and larger and larger, number of bits become more and more and more. Okay? So I am able to capture the fact that something is on the increase. There is some quantity which is on the increase here. As the quantity increases here, the labor also increases. Okay? In sorting, 10, 50, 1000, 20,000, similar number of comparison will be again increasing correspondingly like that. Okay? But here you are going to use number of bits as the measure. Therefore, the notion of input size is very subtle. In fact, if you dig little deep, you will even touch upon information theory. Why? I will briefly hint on that. I am not going to go to the details of it. You view the problem solving process as information manipulation process. In fact, computers are also known as information processing system. So ultimately, you have some information represented, and those representation are manipulated, and some other information is generated. Okay? Therefore, a very realistic way of quantifying the input is the quantum of information in the data. So a realistic measure is going to be intimately connected with information theory and so on. The entropy will come into picture, etc. But we will not go into that level of detail because that is not necessary. For all our practical purposes, the following two notions of input sizes is sufficient. Okay? What are the things? Typically, input size could be number of items if this number varies. If number of items is fixed, much like your GCD algorithm, you always take two numbers, but their values change. Okay? If number of items can be used as an input size, it can be used to measure the quantum of input if it varies. If it doesn't vary, if not, number of bits needed to represent the input. This can be used. So these are the only two measures that we are going to use for all practical purposes, except for extremely complicated and advanced technical requirement, like for example cryptography. In cryptography, there is no information leak. The secrecy is maintained, right? The encryption is guaranteed to leak no additional information. That means you have to appeal to the information theoretic level and then build the mathematical argument. But for all our day-to-day computations that we are doing,